Dear friends, this is the lecture number 1 of fourth chapter of your NCERT book, Moving Charges and Magnetism. Also you can tell this chapter Electromagnetism. Also you can tell magnetic effect of electric current. So it's a long chapter, but today we'll discuss in this chapter how a current carrying conductor behaves like a magnet. When current passes through a conductor, the conductor behaves like a magnet. But who is the man who first told this and also experimentally show to the whole world that a current carrying conductor behaves like a magnet? That man is Oersted. Oersted is the man who first told when current passes through a conductor, it behaves like a magnet. If only we tell something to the peoples, to the world, then everybody will believe us? No. We have to show by experiment. Also in lower classes you have done the experiment how current passes through a conductor. When current passes through a conductor, how it behaves like a magnet. You have done in lower classes taking some iron fillings to a current carrying conductor. The iron fillings get attracted by the conductor. You all have done that in lower classes. But what experiment Oersted did and show to the whole world that the current carrying conductor behaves like a magnet. Oersted did the experiment like this. Oersted now take one conductor and apply current to it by the help of a battery. The battery is required because current will pass in a particular direction. And if it behaves like a magnet, it must deflect another magnet. So he took one magnetic needle. He took one magnetic needle here. This is a magnetic needle. Okay, so this magnetic needle, it is just below the current carrying conductor. South pole of the needle here, north pole of the needle here. Like this he kept it. Initially no current was passing in this. One switch, suppose we will keep one switch here. When the switch is closed, suddenly current starts flowing through this conductor in this direction. Means from south to north of the magnetic needle. This side is south, this side north. Current is flowing from the south to north of the magnetic needle but along the conductor. When current starts flowing along the conductor from the south side to the north side of the magnetic needle, immediately what happened? The needle gets deflected and the needle deflects like this. You see the deflection of the needle. Needle deflects like this. This north pole gets deflect towards west. If this is the conductor, you see this is the conductor current pass and this is the needle just kept below it. Just kept below it. This red cap is the north pole. The north pole deflects like this. You mark now. The north pole deflects like this towards west. Okay, this side is west. My left hand side is west. Right hand side is east. So north pole now deflects towards west. So when the magnetic needle deflects, then it's sure there is some other magnet nearby. And nearby which magnet is there? This current carrying conductor. The current carrying conductor, then it is proved that it behaves like a magnet. When the direction of the current is reversed, when the battery terminals change, then the current will flow in this way. When direction of a current reverse, the needle deflects in the reverse way. You see, when current passes like this is the direction of current. This cap side is the direction of current, blue cap side. Then this is the north pole. Initially kept like this. The north pole deflects like this. See, north pole deflects like this. But when current passes in this direction, north pole deflects like this. And when switch is off, no current passes through this conductor, there is no deflection of the needle. Then Oersted proved a current carrying conductor behaves like a magnet by this small experiment. But where the direction of the needle deflects, where the needle deflects, in which direction, that is given by two rules. What are the two rules? The first rule is snow rule. Snow. The full form of snow is south, north over west. South, north over west. If you write it completely, you say south, north over west. This rule tells the direction of deflection of the needle. How? It's like this. When current passes through a conductor, from south to north, of a magnetic needle kept below the conductor. When current passes through a conductor from south to north of a magnetic needle which is kept below the conductor, then the north pole of the needle is deflected towards west. The north pole of the needle is deflected towards west. You see, SNOW. When current passes from south to north along a conductor kept over a needle, O stands for over. Current passes from south to north along a conductor kept over a needle, the north pole is deflected towards west. South, north over west. You can write it like this from the full form, from let's see SNOW. When current passes from south to north along a conductor kept over a needle, then north pole is deflected towards west. SNOW. Also it can be determined by Ampere's swimming rule. Same thing. Also it can be determined by Ampere's swimming rule. What is this rule? Ampere's swimming rule. It's like this. If one swims, you see, one swims. I am drawing the figure of a person who is now swimming. This is the direction of current. When one swims, this is the person who swims. Okay. When one swims, you see the person is swimming. Clear? Drawing is not good, but it's a person. You see, is swimming along the current. When a person is swimming along the current, swimming like this, along the current, keeping his face towards the needle, means face is downward. Face is downward like this. Face will be downward. Keeping his face towards the needle. Then right hand will be in this direction. Left hand will be in this direction. The north pole is deflecting towards which hand? Right hand or left hand? Left hand. I am telling you completely, it's this one. When one swims along the conductor or along the direction of current, when one swims along the direction of a current, keeping his face towards the needle, the north pole of the needle is deflected towards west. The same rule, same thing. Okay, in this way, Oersted proved that a current carrying conductor behaves like a magnet. But Oersted didn't give the expression of magnetic field. Just like electric field, you have read in the first chapter, electric field intensity, the strength of the electric field means the force per unit charge, force per test charge, the strength, intensity of electric field. Here, if current passes through a conductor, it behaves like a magnet. Also, it provides us a magnetic field around it. If it is a conductor, current is passing, it has a magnetic field around it. Then where the strength is more, where the attraction is more, that I want to know. But Oersted didn't give any expression of that magnetic field strength or magnetic field intensity. Then who gave the expression? Biot Savart. Biot Savart then gave the expression of magnetic field. The next law comes here, Biot Savart's law. Now we'll discuss. So Biot Savart's law. Okay. What this law tells? I told you this law provides the magnitude of magnetic field intensity, the expression of magnetic field intensity, but not due to a conductor. Not due to a conductor. The expression is given by Biot Savart law, but due to a small element. What do you mean by that small element? Try to understand. So this is the, suppose conductor X, Y, current is passing like this, I current is passing through this, but this expression provides the magnetic field due to only small element like this. You see, this is a small element, AB is a small element. So this small element we can present by dl vector. So it is also a vector quantity. I am showing you that vector. You see, this is the dl vector. Vector quantity, this is dl vector. Small element is always a vector. Okay, very small, infinitesimally small. This is dl vector. So small element, this is dl vector. But when current passes through this small element, then it is called as a current element. What you understand? Current plus small element. This is called as current element, or we can write this as I dl vector. Dl vector is a small element, but when current passes through it, it's called small element. I dl vector. Current is which quantity? Scalar vector. Scalar quantity. dl vector I am telling it's which quantity? Obviously vector quantity. So current is a scalar quantity, but current element is which quantity? Vector quantity. Again I am telling you another question. Current density is which quantity? Also vector quantity. You have read in the previous chapter current electricity, current density. Current is a scalar, but current density is a vector, current element is vector. And Biot Savart gave the expression for, not for the whole conductor, but for this current element. For a small part of the conductor, they gave the expression, not for the whole conductor, for a small part of the conductor, which is called current element. At a point, the expression is given at a point. Suppose that you take this point is P, and we have to join that point with the position vector. This is the position vector. R vector is the position vector. Between DL and R, one angle is made, that is theta. That is also important. Here theta has also a big role. That is the theta. Theta is the angle between DL vector and R vector. R vector is the position vector. But according to Biot Savart, the magnetic field at point P depends on which factors you see. dV. Why I wrote the magnetic field dV? Because it is given by a very small element. So I also wrote the magnetic field small. dB. B means magnetic field, but dB means small magnetic field. As this is small element, also I wrote here dB. So this small element dB directly proportional to I. More current pass, more magnetic field. Directly proportional to dl. More is the length of the conductor, more is the element, more is the magnetic field. Also directly proportional to sin theta. Sin theta. And inversely proportional to r square. Depends on these four factors. Now we'll combine them. If I combine, so dB is equal to, so here k I dl sin theta by r square. But what is this k? What is this k? Proportionality constant. What is the value of this k? This k is equal to mu naught by 4 pi I dl sin theta by r square. This k is mu naught by 4 pi in SI units. If you take SI unit, this k expression k value is mu naught by 4 pi. What is this mu naught by 4 pi? What is its value? I am just reminding you Coulomb's law. This Biot Savart law, it is just the similar thing like Coulomb's law. Coulomb's law you have read in electrostatic chapter, and this is the magnetism chapter, the first law, Biot Savart law. There is much more similarity between Coulomb's law and Biot Savart law. Coulomb's law gave the expression of electric field. Electric field, force then alternate to electric field, and Biot Savart law is giving the expression of magnetic field. That gives electric field, this gives magnetic field. That also depends inversely with a square, inverse of square law. This is also inverse of square law. Inversely proportional to square of distance. Okay, there is a lot of similarity. And there was also one constant k, 1 by 4 pi epsilon naught. Have you remembered? 1 by 4 pi epsilon naught, that constant. 9 into 10 power 9. The same thing you see here, similarity. 4 pi is there, 4 pi is here. Only thing is epsilon naught was in denominator, but here mu naught is in numerator. What is epsilon naught? Electric permittivity of free space, vacuum. And similarly mu naught is, that is electric permittivity, mu naught is magnetic permeability. Magnetic permeability of free space. So if we experimentally, this value is 10 to the power minus 7. Its experimental value is 10 to the power minus 7 in SI unit. SI unit you write. In SI unit. This is the value of mu naught by 4 pi. So Biot Savart, according to Biot Savart, the expression of dV finally is, remember this one, mu naught by 4 pi I dl sin theta by r square. Where mu naught by 4 pi is 10 to the power minus 7, like 1 by 4 pi epsilon naught. I told you the similarity between them. Then what is the value of mu naught? 4 pi into 10 to the power minus 7 in SI unit. Okay, so this is about the Biot Savart law expression. But now discuss as theta is here, which is the dissimilarity between Coulomb's law and the Biot Savart law. In Biot Savart law, magnetic field depends on theta. But in Coulomb's law, is there any theta? No theta. That in Coulomb's law, electric field is independent of theta. But here, the magnetic field depends on theta. As theta is here, we will not leave without discussion of special cases. So let's come to case 1 now. Case 1, theta is equal to 0 or 180. As sine 0, 0, sine 180 also 0. I discussed the cases combining. So what about dB? dB is equal to 0. What? dB is equal to 0. What do you mean by this? If you find magnetic field on the small elements, if the P point will come here, You see, on the small element, if I find magnetic field here, I will find magnetic field here, on the small element, or here also, below it. On the small element, anywhere you want to find magnetic field, its value will be 0 due to the small element. Magnetic field value will be 0 on the small element. From that I will tell you, suppose this is a conductor. Anywhere you take a small element like this. So on the conductor, magnetic field is always 0. On the conductor, on the line of the conductor, straight conductor, magnetic field is 0. This one will help you to solve the numericals of this chapter. Remember this one. Along the conductor, magnetic field is always 0. This case tells. Now come to case 2. Case 2, theta is equal to 90 degree. So this is dB is mu naught by 4 pi I dl by r square. And this is maximum. If 90 degree, this magnetic field will be maximum. This is about special case of Biot Savart law. I only told you to get this idea that on the line of the conductor, magnetic field is 0. Now let's come. This dV, magnetic field is a vector quantity like electric field. If it is a vector quantity, so we will not leave it without writing it as a vector form. Let's come and write it as a vector form. So how will I write it as a vector form? dV, now let's see, this is the expression of dV, I dl sin theta by r square. I dl sin theta. What happened? I dl sin theta. When sin theta comes, immediately it comes to your mind of some product of vectors. Cos theta, sin theta, product of vectors. A vector dot B vector, AB cos theta. A vector cross B vector, that will be sin theta n cap. Okay, from that I think it is coming some idea. As sin theta is there, so can I write this is I vector cross dl vector. As sin theta is there, it will be cross product I vector dot cross vector mod, because no vector now is there, so I am taking it as a mod into r square. We can write dB like this in this vector form. I vector cross dl vector with a b sin theta. So I vector cross dl vector divided by r square. Understand? If you understand this one, then I will tell you have no previous knowledge about the vector. You have not read the vector clearly in class 11th. I have already done one blunder mistake here. Can you able to mark what mistake I did? I only want to show you that students generally do this type of mistake. It's a very common mistake. Now you see what mistake I have done. See here. Pause the video and see what mistake I have done. Then you find the answer. Then again you play the video. What mistake I have done here? You ask yourself. I have taken current as a vector. Is current a vector quantity? Is current a vector quantity? No. It doesn't obey the vector algebra. It's not a vector. Okay. So I cannot write like this. It's a common mistake always done by students. I hope you will not do. Just I show you. So this is to make a vector what will do. Then it cannot be written as AB sin theta, but we will write it as a cross product. Anyhow, we will write it as a cross product and we will bring there AB sin theta. How will we bring AB sin theta? Let's multiply one R. Let's multiply one R in the numerator, in the denominator. See, I multiplied one R in the numerator, one R in the denominator, it becomes R square into R cube. So it is now mu naught by 4 pi I. Now it becomes AB sin theta. Any problem? DL is vector. R is also vector. I can write DL vector cross R vector mod divided by R cube. So this is now dV. Now the vector product is correct, I think. No mistake? Okay. But if you want to write in vector form, I will remove the mod here. I will write dp vector. If I write vector symbol in LHS, so then dl vector cross r vector, I remove the mod sign there. So this is the complete vector form of Biot Savart law. Vector form of Biot Savart law. In exam, the question comes: state Biot Savart law and write its vector form. Then you have to write it like this. But from the vector form, you mark one thing: db vector is the cross product of dl and r. So db vector must be perpendicular to dl vector and db vector must be perpendicular to r vector. We got two pairs of perpendicular vectors here. You know, in cross product, a cross b is equal to c. C is perpendicular to a and c is perpendicular to b. Okay, so here db vector perpendicular to dl vector and db vector perpendicular to r vector. Understand? This is also another dissimilarity comes between Coulomb's law and Biot Savart law. What dissimilarity? In Coulomb's law, electric field acts along the position vector. Electric field acts along the position vector. E is equal to 1 by 4 pi epsilon naught q by r square into r cap. E vector is equal to r cap. It acts along the position vector, but magnetic field is perpendicular to position vector. This is another dissimilarity between Coulomb's law and Biot Savart law. There is some dissimilarities and some similarities between Coulomb's law and Biot Savart law. This can be asked as a question also in exam, to write similarity and dissimilarity between Coulomb's law and Biot Savart law. Already I have told you all these things. Okay, so this is about the Biot Savart law now. But using this Biot Savart law, we can find the expression of magnetic field due to a current carrying circular coil. We can find it at its center. Also, we can find at any point on the axis of a current carrying circular coil, which is a very, very important derivation. Very important derivation. At any point on the axis of circular coil, you take a circular coil. This is the circular coil. Current is passing like this. See, this is the center O. Let's draw its axis. We'll find magnetic field at point P, which is at a distance. We can take the distance as x. Along x-axis, I am taking this one. I am taking this one along x-axis, and this line I have to make straight, and this is y-axis, and this axis you can make it as z-axis. Okay, you can make it as z-axis. Now the coil is like this. Coil is like this now, perpendicular to x-axis. Coil is in yz plane, perpendicular to x-axis. So what happened here? Now you see, if the coil is like this, current pass in this way, we will find magnetic field at this point, which is at a distance x from the center of the coil. How will do? By using Biot Savart law. I am saying you, now you see, I am showing you the coil. You see, I have collected this coil. It's not actually a conductor, but just I am showing you here. It looks like exactly the coil is like this. Current is passing in this way. Okay, current is passing in this way. Current pass and comes out here. Here you see, when current comes out, this axis. See, totally like this. This axis at this point we will find. This is point P. This is point P, and the current is passing like this and comes out. Okay, so this is about the coil. We will find the magnetic field here. What we have to do? We know Biot Savart law. That is only valid for a small element. We have to first choose a small element. We will write Biot Savart law for that small element. Then we will proceed our derivation. Means For small element, we will write the expression, then integrate it. This is the overall derivation. For small element, choose the small element, write the expression for it, then do integration. This is only the derivation. Now let's see. So when current is passing like this, here you consider the small element here. Suppose here is the small element A, B, I choose. Here current passing this way. See, current passing this way. This is the small element dl vector. This is the small element I choose. There dl vector means practically I am showing you because it's as in 3D. Current is passing in this way. This is the small element. I choose the small element like this. You see. This is the dl vector. Current is passing like this, and this is the dl vector. Dl vector, that's a very small part will take here. Very small part will take a very small part here. If it is a very small part, current is passing like this. So this is the small element. Understand? Okay, practically you can able to understand what the small element. Okay. Now at this point we find from the small element you just compare this diagram. This is the small element. From the small element we have to join the point P, that is the position vector. From the small element let's join to P, that is the position vector. Position vector is like this. This is R vector. Understand? So this is the R vector for position vector. Now write the expression of dV according to Biot Savart law. Everything you got. Take the radius of the coil as R. I is the current passes through this coil. X is the distance of point P from the center, and position vector is R vector. So you will use here now Biot Savart law. If we use the Biot Savart law, using Biot Savart law for the small element, you see dB equal to mu naught by 4 pi I dl sin theta divided by R square. Our R, also this is R, using Biot Savart law. But what is the value of theta here? What is the value of theta? That is important to know. What is the value of theta here? The value of theta, how much you will tell me. Can you mark any value of theta between R and dl? From this 2D diagram, you can be able to tell the value of theta from this 2D diagram, because this is 3D is done on 2D on a plane, so you can be able to know the theta. So I am showing you practically. You see, this is the coil. Current is passing like this, so this is the small element. You see, this is the small element. Current is passing like this. From the diagram I am doing, this is the small element. Understand? Okay. Can you mark? This is the small element, and this is your axis. See, this is your axis. This is the small element. This is your axis. I think it is difficult for me to handle the all. Okay, this is the small element. This is the axis here, and this red marker now playing the role of a position vector. This is the point P. Black marker tip. This is the point P. This is the small element. This is the coil, and this plays the role of position vector. See, this is the role of position vector. You see now. This is the dl vector. This is the dl vector. This is the x-axis, and this play the role of. I am handling it like this. See, this is the position vector. This is the axis. Black marker is the axis. Red marker is the position vector, and red marker is the position vector, and the blue marker is the dl vector. See, between the red marker and blue marker means between R vector and the dl vector. What is the angle you see? Can you able to mark the angle? Can you able to mark the angle between dl vector and R vector? See here. If this one you will tell, then it's a great achievement for me. From this practical thing, if you can able to find, this is the dl vector. Okay, this is the R vector. dl is blue marker, axis is black marker, and this is the red marker is the R vector. What is the angle between them? The blue marker and the red marker. It's now I think already clear to you. What is the angle? Which angle I am telling you? Between red marker and the blue marker. What is the angle? It's very clear, it's 90 degree. It's very clear, it's how much degree? 90 degree. Okay. So it's a 3D diagram. So it's very clear that it's 90 degree. If this is 90 degree, you put it here. Mu naught by 4 pi I dl sin 91, then this is r square. Sin 90 is 1. Theta is 90 degree. Since theta is equal to 90 degree. This is the dB. But where is the direction of a dB vector? I have told you dB is perpendicular to dl and perpendicular to r. So this is r vector. So dB is perpendicular to r. This is the dB vector. And how it is perpendicular to dl? It is automatically perpendicular to dl because dl is perpendicular to this whiteboard along z axis. dl is perpendicular to this whiteboard. Okay, this is the dl vector. Perpendicular to the whiteboard, the coil is kept like this. dl vector is perpendicular to whiteboard means it is already perpendicular to dB. dB is perpendicular to both dl and r vector. So how I will find b? Now b is equal to integration of dB. We'll do like this. B is equal to integration of dB? No. If we do like this, then we'll face problem. Mistake will be there. So this dB can be resolved into two rectangular components. You see, one component in this direction, another component in this direction. This was the x-axis. So if this angle is theta, then here which angle is theta? This is to this line, this is perpendicular, to this line, this is perpendicular, then this is also theta. Between two lines, if angle is theta, between their perpendiculars, angles also theta. Geometry theorem. It's very easy to find angle. Between two lines, angle is theta. Between their perpendiculars, also angle theta. To this axis, this is perpendicular. To this r vector, dB is perpendicular. This is also theta. So this is dB cos theta. Which side theta is there? That will be cos. And this is dB sin theta. So dB vector is now resolved into two components. But if I will take another small element here, this current element will be in this direction. Then if you join it here to this point, again we will get a dB also in this direction. This is dB, dB dash. I can write dB dash, but dB and dB dash will be same because everything is symmetric. dB and dB dash will be same. Also your dB dash will provide two components. One component will come like this, one component will go like this. Again this is cos theta because this angle will also be theta. This is dB cos theta, this is dB sin theta. Which component will be cancelled? If I take just opposite element to this AB, which component will cancel, sin or cos? dB cos theta is cancelled. But you can write in one line, dB cos theta is cancelled due to symmetry. Over in one line. To which component only remain? dB sin theta. So our integration is not to dB but to dB sin theta because one part is already cancelled. We'll do the integration to only one part, that is dB sin theta. dB you put here mu naught by 4 pi I dl by r square sin theta, only mathematics, mu naught by 4 pi, physics part already I have completed, r square, but sin theta is how much here? You see, sin theta is r by r. So it is now mu naught integration I left. So it is now mu naught by 4 pi constant, it will go outside, I is constant, capital R is also constant, this become r cube which is also constant, integration of only dl. Now integrate dl. What is the integration of dl? dl integration means it is whole conductor, whole circular coil. Okay, so means its integration whole circular coil circumference, it is 2 pi r. 2 pi r. So now see what is the expression of dB it is coming. If I will consider two small elements at a time two small elements I will take, then this will be 2 dB sin theta. because dB sin theta, and due to this one also dB sin theta will come. Here it will be 2 dB sin theta. You can proceed this one, and the integration of dl will be half circumference, means only pi r. Same thing, you can bring the 2 from here, or you add the 2 at last, taking only one component from one small element. Okay, you understand? Because some books are doing here, considering directly to the small element at a time, there are 2b sin theta, then they proceed and integration is pi r. But I consider only one small element, dB sin theta, and I did the integration over the whole loop and I wrote 2 pi r. So this is mu naught by 4 pi I, this is pi, 2 pi, this is r, capital R. We have done a mistake here, capital R, because circumference r is the radius, capital R. So this is pi r square divided by 1, 2 remain here also, r cube. But in case of small r, I can write r square plus x square root over, then whole cube. So it is mu naught by 4 pi 2I. What is this pi r square? A is area of the coil. A is area of the coil. R square plus x square root over means half power. It becomes 3 by 2. Sorry, I wrote here dB. This is B because integration is already over. So this is the B here. So this is the magnetic field B. So expression of the magnetic field B is mu naught by 4 pi 2 Ia divided by r square plus x square power 3 by 2. But for n number of turns, if this coil will contain capital N number of turns, many turns will be there, this expression will be 2. I will multiply the term here, r square plus x square power 3 by 2. You have to remember this expression. You have to remember this expression of a magnetic field. How will you remember? Very simple to remember. B is, I am telling one trick, B is mu naught by 4 pi. Mu naught by 4 pi you will always remember. 2 NIA, Nia. Mu naught by 4 pi 2 Nia. 2 Nia by r square plus x square power 3 by 2. You just remember. But it like this, mu naught by 4 pi 2 Nia NIA divided by r square plus x square 3 by 2. This is the expression of magnetic field at any point on the axis of phase of black coil. We will not leave it without discussing the special cases. We must discuss the special cases. First come to case 1. When this comes as a derivation, one case will be most attached in the derivation part, and which case I am discussing first, that one is most important case, always comes in attached question to this long question. When x is very large, this p point is very large, far away from the center, x is very greater than r. At that time we can neglect this r square. R square tends to 0 because r is very small. In that case, B equal to mu naught by 4 pi 2 Nia divided by r square tends to 0, x square into 3 by 2 become x cube. It becomes x cube. So in place of Nia, I can write here 2 m by x cube. You see what magic now happens here. In place of Nia, I wrote here m. Means m is equal to Nia. What magic happens here? Have you seen this expression anywhere? This type of expression have you seen anywhere? Yes, you have seen. Where you have seen? You have seen this expression. 1 by 4 pi epsilon naught. You just recall 2p by r cube. You compare this one with this expression. 1 by 4 pi epsilon naught, electrostatic circle, here mu naught by 4 pi, 2, here P, electric dipole moment, here M, magnetic dipole moment. Magnetic dipole, this electric dipole moment, this magnetic dipole moment, this distance cube, this is distance cube. I just change the symbol, no problem, distance cube. Everything is same. Means this expression, this is the expression of electric field intensity due to electric dipole. at any point on the axial line. This is the expression of magnetic field intensity due to circular coil, but similar to electric dipole. So current carrying circular coil behaves like a magnetic dipole. Current carrying circular coil behaves like a magnetic dipole. In exam question you come, prove that current carrying circular coil behaves like a magnetic dipole. If this type of question will come, what will write? You will write this much, and you write this expression is similar to the expression of magnetic field due to a magnetic dipole. This is the expression due to a magnetic dipole. Just like electric dipole, there is also magnetic dipole, similar expression. So current carrying circular coil behaves like a magnetic dipole, where dipole moment M is equal to Nia. We will calculate the dipole moment like this. M is equal to Nia, Nia. Then the question is coming to your mind, if it behaves like a magnetic dipole, so where are the two poles? This is the circular coil. Where are the two poles? So at which side current pass in clockwise direction? That is the south pole. See, at which side current is passing in anti-clockwise direction? See, that is the north pole. See here, anti-clockwise direction north pole and clockwise direction south pole. Then you see this is the coil. At which side current is passing clockwise? That is south pole. At which side current is passing in anti-clockwise? That is north pole. Now the question is coming to your mind. In one coil, how current pass both clockwise and anti-clockwise direction? This type of question comes to the mind of the students. How current pass in both clockwise and anti-clockwise direction in one coil? You see, I am showing you the magic. So if you want to see, you just take a circular coil like this, and you will hold the circular coil. All of you will do at home this one. Then your doubts will be clear. If you have the doubt in that, you will hold it like this, and I am showing you now. This is the direction of current flow. I am taking the pen. From your side, you will see clockwise direction. This is the clockwise direction of current flow. Current flow like this. If the current is flowing like this, if the current flowing like this, from my side it is clockwise. From my side it is clockwise. But you keep somebody in front of you, maybe your little brother or sister or mother or father, anybody you just keep in front of you. Hold the circular coil like this. If the current is passing like this, it is clockwise from my side, but from that side who is standing in front of me, if you ask him or her that you tell me that in which side current flow, if you ask him or her, then when you will tell clockwise, then he or she will tell anti-clockwise. And you do the finger like this. Do the finger like this and ask, from my side it is clockwise, from your side it is what? Obviously that person will tell anti-clockwise. When from my side is clockwise, from the opposite side it is anti-clockwise. You can test it at home. So when from my side it is clockwise, so my side is now south pole, but the other side is now north pole. This side is south pole, this side is north pole. So in one coil, two poles are possible. One side south, one side north. Okay, you can do it also at home if you can able to understand. So in this way, a current carrying circular coil behaves like a magnetic dipole. We can also discuss another case. Case 2 here. Case 2 also we can discuss. See, case 2. Case 2, what happened here? At the center. At center. What is the value of x? 0. Put it here. What will get? Mu naught by 4 pi 2 Nia by r cube. But for one term, if I write, for one term I will take n is equal to 1, only one term, and a value I will put by r square by r cube. So in shortcut we will get here, it will cut everything, mu naught I by 2r. This is the magnetic field at the center of a circular coil. center of a circular coil, this is the magnetic field you will find. So when current passes through a circular coil like this, at its center magnetic field is mu naught I by 2r if r is the radius. But where is the direction of magnetic field? Where is the direction of a magnetic field? That can be determined. At the center, where is the direction? That can be determined by your right hand thumb rule. You see how I am applying? Just finger curling is the direction of current. Do it. Finger curling is the direction of current. You make a round shape on your copy and you see finger curling is the direction of current. Where is the thumb? Thumb is inward. You see thumb. Thumb is inward. The direction of thumb inward means the symbol is like this. Perpendicular to the plane inward. But if the current passes like this, at the center, where is the magnetic field? See, finger curling is like this. Okay, if your finger curling is like this, where is your thumb? Thumb is outward. Outward means dot symbol. This is the expression of magnetic field. This is the direction of magnetic field. Perpendicular to the plane outward. So this is the magnetic field at the center of a circular coil. Also, you can find directly the magnetic field at the center of a circular coil. How directly? You can take a circular coil, we can discuss it in another application. So, you can take one circular coil, you can provide current to this circular coil like this, I current pass and I current comes out. If you want to find center, directly we can find center of coil, circular coil. This is the radius or this is the small element in B. It's a very simple one. This is the dl vector. If you find here, then this radius acts as a position vector. For this small element you apply Biot Savart law, mu naught by 4 pi I dl sin theta by r square. But r is here radius. But what is the value of theta here? 90 degree. So you can put 90 degree. So mu naught by 4 pi I dl by r square. Sin 90 is 1. Then b is direct integration of db. All the constant you can take to outside. Mu naught by 4 pi I by r square. Only integration of dl remain. So mu naught by 4 pi I by r square. But the integration of dl, the whole circumference, that is 2 pi r. And if you cut everything, you will get mu naught I by 2r. This is the expression which we got as a special case from the axis. Also we derive at the center of the circular coil. But if this is a semicircle, if it is a semicircle, current is passing like this. See, for the expression, it is a half. This was mu naught by 2r. For the whole, for the semicircle, it will be 4r. Remember, for the semicircle, it will be mu naught I by 4r, half of the circle. If it is arc, not completely circle, you want to find it at the center. And the arc is making theta angle, suppose here. Current is passing like this. How will you find magnetic field? Very simple. This is, you can use unitary method, mu naught I by 2r. For 360 degree angle, for 360 degree angle, mu naught I by 2r. For theta angle, how much? Mu naught I by 2r, theta by 360. You can find the expression magnetic like this. For whole 360 degree, mu naught I by 2r. So for theta angle, mu naught I by 2r, theta by 360. This is the magnetic field due to an arc. So after getting these formulas, you can able to find the different numericals you can do for the different type of shape of conductors. I hope you will try the different type of numericals you can do. This is the question. Okay, when I current pass, suppose this radius is 2 meter, current is 2 ampere, you can find magnetic field here. This is one question I am giving to you to try. So today we discussed Biot Savart law and its applications to find magnetic field at any point on the axis of circular coil and at the center of the circular coil. Thank you.